Hi, and welcome to this video on the topic of nuclear fission and fusion. The words fission and fusion often confuse and scare students in equal measure, but by the end of this video you'll be a pro. Plus, as a bonus, you'll be able to explain how nuclear power stations, nuclear weapons, and the core of the sun work. Isn't physics wonderful? So far, we've seen that an unstable nucleus can undergo alpha, beta, gamma, or neutron decay. There's actually another special type of radioactive decay which only happens to a few very heavy nuclei, nuclear fission. Fission is the splitting up of a large and unstable nucleus, such as uranium or plutonium. When fission occurs, the large nucleus breaks up into two smaller nuclei and 2 or 3 neutrons. Energy is released in this process, so the products have kinetic energy, and some gamma rays are emitted too. Spontaneous fission is rare in nature, so if we want to use fission for anything, we have to make it happen. The way we do that is by allowing a neutron to bash into a heavy nucleus. Let's look at an example. Here, a uranium-235 nucleus has absorbed a neutron. This causes this nucleus to become very unstable and break up almost instantly. It breaks up into 2 lighter nuclei, barium and krypton, and 2 neutrons. Note that the 2 here just tells us that there are 2 neutrons released. We could have written this instead, but it would have taken up more space. We can see another possible fission reaction for uranium-235 in this example. Why don't you pause the video now and have a go at working out the values of x and y. For x, we should remember that the total mass number on the left must be equal to the total mass number on the right. So the first line should look like this: 235 plus 1 equals x plus 92 plus 3. Remember that that big 3 means that there are 3 neutrons emitted. The next line then is 236 equals x plus 95. So x must be equal to 141. Working out the value of y is even easier than this. On the left hand side we have 92 plus 0, and that must be equal to 56 plus y plus 0. So doing the algebra, that gives us an answer for y of 36. So far, we've only looked at what happens when a single uranium-235 nucleus is present, but what happens when we have lots of these nuclei close together? As we know already, when a neutron bangs into a uranium-235 nucleus, it can cause it to undergo fission, splitting into 2 small nuclei and 2 or 3 neutrons. If any of these neutrons go on to bash into another uranium-235 nucleus, they can cause the same thing to happen again. Neutrons released by this second reaction can go on to cause further fission. We call this a chain reaction. In your exam, you could be asked to draw a diagram like this from memory and to explain it, so it might be a good idea to pause the video here and make a few scribbles. Nuclear fission can release huge amounts of energy. If a chain reaction is uncontrolled, most of the released neutrons can go on to cause further fission reactions, and the rate at which energy is released can increase very rapidly, with devastating consequences. This is what happens inside a nuclear weapon. In a controlled chain reaction, just one of the neutrons from each fission goes on to cause a further fission reaction on average. This means that the power output of this process is predictable, which is why controlled fission is used in nuclear power stations. This diagram shows how one type of nuclear power station works. The part that contains the radioactive material is called the reactor. Here, the reactor takes up the left half of the diagram. As you can see, it's surrounded by thick concrete to protect workers from the harmful gamma rays and neutrons which are emitted inside it. The fuel rods are made mainly of uranium-238, but contain a small amount of uranium-235. Uranium-238 is the most common isotope of uranium, but it's only uranium-235 that will release energy by fission. When a uranium-235 nucleus undergoes fission, one or more of the neutrons released can go on to split up a different uranium-235 nucleus in a neighbouring rod. The rate at which fission energy is released inside the reactor is carefully monitored. If it gets too high, the control rods can be lowered down further into the reactor, which will decrease the reaction rate. The control rods are normally made of boron or cadmium, because these materials are very good at absorbing the neutrons that allow the reaction to continue. In the event of an emergency, the control rods are lowered down fully into the reactor to stop the chain reaction completely. Everything else about how a nuclear power station works is almost identical to how a coal, oil or gas-fired power station works. In this power station, cold gas is pumped into the reactor core, where it's heated by the energy released by the nuclear fission reactions occurring inside. Inside the heat exchanger, this hot gas heats up the cold water that's coming in from the right and turns it into steam. This steam then goes on to turn the turbines and generators which produce electricity. Nuclear fusion can be thought of as the opposite process to nuclear fission. In fission, a heavy nucleus breaks apart into smaller pieces, and in fusion, two light nuclei join together to form a heavier nucleus. Like fission, fusion also releases energy, and potentially quite a lot of it. Let's have a quick look at what happens when two nuclei fuse together. Because of the protons they contain, each of these nuclei is positively charged. When we try and bring them closer together, the force of electrostatic repulsion between them gets stronger. Here on Earth, because the temperature isn't high enough, nuclei aren't moving fast enough to overcome this electrostatic repulsion, and they'll be repelled away from one another before they get close enough to fuse. For this reason, fusion doesn't occur naturally on Earth. It does occur in the Sun though. The temperature in the core of the Sun is around 15 million degrees. There, as you might imagine, nuclei are moving very fast indeed. The energy released in the countless fusion reactions in the Sun's core is what allows it to constantly beam colossal amounts of light energy out into space, and ultimately what sustains life on Earth, including your life and mine. You have to admit, physics is kind of useful from time to time. One of the fusion reactions that occurs inside the Sun looks like this. Two isotopes of hydrogen, hydrogen-2 and plain old hydrogen-1, fuse together to form helium-3, releasing energy as they do so. If we were able to use controlled fusion to produce our electricity, it could solve the world's energy crisis. Fusion doesn't release CO2, and so wouldn't contribute to global warming. It wouldn't have many of the serious dangers involved with the running of a fission-based power station, and the source of fusion fuel is plentiful, as the hydrogen needed could be extracted from seawater. Unfortunately, building a working fusion power station is remarkably difficult, and could take 10 to 50 to 100 years, depending on who you talk to. Let's go through another quick example now. For part A, the answer of course is fusion or nuclear fusion. In part B, to work out the unknown particle, we need to work out its mass and atomic numbers. The mass number first will be equal to 5 minus 4, which gives 1, and the atomic number will be 2 minus 2, which gives 0. So of course the only particle that can be is the neutron. One last short section now for this video, and for this entire topic. So far, we've looked at both fission and fusion, and how both processes release energy, but where does this energy come from if all we're doing is breaking something apart or putting two things together? To explain, let's have another look at this fusion reaction. We can see here that the sum of the mass numbers on the left is equal to the sum of the mass numbers on the right, and the same goes for the atomic numbers. That just means that we finished off with the same number of protons and neutrons we started off with. Sounds about right so far. If we were to actually measure the total mass of the reactants, then the total mass of the products, we might be in for a bit of a shock, because we'd find that the products weighed slightly less than the reactants. In other words, a small amount of mass was lost in the reaction. This is all very perplexing, until we understand the famous equation E equals mc squared, which tells us that mass and energy are basically made of the same stuff. The mass lost is actually converted into pure energy. The exact same thing happens in a fission reaction. A small amount of the mass of the reactants is converted into energy, which is why the products weigh slightly less than the reactants. So there you go. Chain reactions, E equals mc squared, and the origin of life itself all in one video. It's like all your Christmases have come at once. Thanks for watching, and good luck.